hopefully you're all become too tired of my face by now. Nicholas gave us a great introduction this morning to terrestrial laser scanning. I think for the next 25 minutes or so I'm just going to expand upon some of the things that Nicholas said with a bit of a case study and maybe a few notes from the case study. I'm going to talk a little bit about the technologies, not too much. Nicholas introduced the concept of frame versus hemispheric scanners, so I'm going to talk a little bit about that, so the practical differences between the two types of scanning systems. And then a plot mensuration study that we did 10 years ago. The concept may have been propagated that terrestrial LiDAR or terrestrial laser scanning is fairly new and in some ways more fresh than airborne. But in actual fact, the technology has been around for over 10 years. We have been playing around with it in forests for a PSP type work for around about the same amount of time. So there you go. And I'll finish off with a couple of slides just to illustrate some of my thoughts regarding the future of TLS and PSP types of work. Okay, so essentially there are two types of TLS, or terrestrial laser scanning systems. Frame-based system, which is essentially like a camera. Scans out horizontally and vertically, and it captures an image in a very similar way to a camera, a frame-based image. And then, of course, you've got the more hemispherical type systems that do that. I'm not going to do exactly what Nicholas did, but they did that kind of rotation in the vertical, and they spin around on a gimbal, on a mount, and so in that way you can get a full 360-degree hemispherical scan. There are pros and cons to those two types of systems. Pros and cons in terms of the data attributes, and pros and cons in terms of their logistical deployment. And we'll get a little bit to that. And then there are combination systems. So there are some systems out there that are essentially a frame-based scanner. So they have a dual-axis scanner. They scan in the X and the Y, but then they're on a pan-tilt mechanism that once they've collected one frame, it'll then move around to an adjacent frame, capture that, then move around again. So it captures frames in sequence, and then it can be tilted and then do it again. So essentially you can capture almost a full 360 degrees with these pan-tilt type sensors and get something that's analogous to a hemispherical scanning system. The precision, accuracy, resolution of these systems is in the millimeter to centimeter range, so you know, at least an order of magnitude better than what we can see with the airborne systems. Every particular sensor that's on the market tends to cater towards a certain market. And so the range that you get out of these things varies from just less than a meter in some cases up to 3,000 meters in other cases. It really depends on the market niche that the sensors are being optimized for. But what you'll find is that most of the scanners that are on the market are in that kind of 100 to 300 meter range because they're for kind of built environment type applications, architectural or physical plant infrastructure type applications. So that's a very large market segment. And fortunately for those of us in forestry, those types of scanners lend themselves reasonably well to being used in forest environments because we deal with similar kinds of scales of features that we're interested in. In terms of positioning, most sensors that are currently on the market either incorporate or they allow for the incorporation of GPS so that you can position them as you're scanning. And some of them even allow the incorporation of inertial guidance systems or an inertial measurement unit, which means you can actually move them. So you can be scanning either a frame scan or a rotating scan, but you can actually be moving the sensor as well at the same time. There's maybe not too many applications of that just yet, but one of them is if you're on a moving platform. If your platform is not perfectly stable, as may be the case if you're on a boat and you're trying to scan an oil rig or something like that, then that can be quite a useful application. Trying to keep a scanner stable when you're mapping something 100 miles offshore can be a little bit difficult. So incorporating an inertial measurement unit in a GPS can actually alleviate the challenges with that. And of course, we've heard quite a little bit about sensor fusion. Most contemporary systems at least have some kind of an imaging system, like an RGB imaging system embedded in them now as well. So even though the technology is more than a decade old now, it has evolved to become much more user-friendly, much more accurate, much more functional than it was a decade or so ago. And as you can see here, there's just a range of some of the technologies are. In the bottom left-hand corner is the echidna that Nicholas introduced this morning. I've worked with the echidna, but the one I'm most familiar with is the Optec Ilris up on the top right there. And interestingly, they both chose yellow. I guess that's a survey type thing. Anyway, they're both very different sensors. The Optec is a frame-based system, the echidna is a hemispherical system. And so what I'm going to do is look at both of these systems a little bit and do a little bit of a comparison of their attributes. So first of all, the frame-based system essentially gives you something that looks like a rectilinear data collection in terms of from the vantage point of the viewer. It's a rectilinear scan pattern. But then if you look at it on in side view, if we scan into the forest with this type of a configuration, what we're going to end up with is a wedge of data. From a single scan, we'll end up with a wedge. So very close to the scanner, we're not going to get much height information. But as you get further away, eventually we're going to encounter the tops of the trees, and so we're going to kind of get a wedge. So what that means is there's a minimum distance that you have to go before you're actually going to get the full height of the trees from ground to the tops from a single scan. But of course, if you can move the scans around and stitch them together, then that maybe isn't so much of a limitation. But that is a limit from a single scan point of view. Now, if we want to utilize this technology, this frame scanning technology, to scan a whole PSP, and then we want to capture that PSP with a uniform density of sampling, there's a couple of things we've got to bear in mind. As we scan into that plot, the density of points reduces. What we see in terms of the upper level of the canopy changes. Obviously, we see more of the upper canopy as we get further away from the scanner, but conversely, we also see less of the upper canopy as we get further away because of occlusion. There's more things in the way. The other thing is it's fairly complex to set up because we've got this this plot, in this case circular plot. I agree with Maury, I like circular plots, makes life a lot easier. We're trying to scan into the circular plot, but we've really got to do it from multiple perspectives. We need to, in order to unify the density of points within that plot, in order to get an even sampling, we have to do multiple scans. Now, the obvious solution is just to scan from one side and the other side straight into one another, but then you start having problems with alignment. It's not easy to align the scans, especially when you think of trying to position those that sensor under the forest canopy. You know, GPS isn't so great on the canopy, as we all know. So, you know, if you're off by even a few centimeters and you try to align the scans, it can be quite challenging. So ideally, you want to be able to align on features or targets. And in order to be able to align on targets, you need to be able to see them at a more oblique angle. You can't align on the same target when you're 180 degrees diametrically opposed, because you don't see the same target. And one of the downsides of scanning into a plot is that you suffer occlusion on the way in. So your density or the features in the middle of the plot are the most compromised, in theory. Now with a hemispherical scanner, of course, and I've got exactly the same diagram that Nicholas illustrated earlier. With a hemispherical scanner, you don't suffer the challenges with regards to density in the middle of the plot. In fact, quite the opposite. You get a very good representation of the center of the plot, but you suffer occlusion as you go out of the plot. And I don't need to talk about these. You saw exactly the same types of images this morning. So just some considerations with regard to that hemispherical configuration is that usually we lose some data right in the middle at the ground level. It's, well, if you think about it, trying to scan all the way around, it's very difficult to scan beneath yourself. You can scan over. So we do lose a little bit of data there, but that's not really a problem in terms of the data that we work with. But this type of a configuration where we try and scan out, capture a full circular plot, can be achieved with a frame scanner as well. As I mentioned, we can move this frame scanner around, we can move the frame scanner up, and we can stitch the whole thing together. It can be done, it has been done. Richard Fournier and some of his students have done a lot of that type of work, but it's difficult to do. It's a lot of time in the field, and it can be a lot of time back in the office trying to stitch everything together. So in that regard, from a logistical deployment point of view, the hemispherical scanners are much easier to use in a forest context. But there's still a question as well, which approach is better? Is the multiple scan looking in a better approach than the single hemispherical scan looking out? And so we did a little bit of a very kind of quick and dirty assessment of that by doing a benchmark comparison of two systems, an ILRIS scanner and a echidna scanner down in Tumbarumba in Australia, and some forest plots there, where we actually surveyed the plots. We had all the field data, we set up the echidna, we set up the ILRIS around it, and did this comparison. Now, this is kind of a work in progress, so there's a lot more things we could do. All we have for now is just looking at the vertical foliage profiles. And so that's what I'd like to show you here now. Now, the echidna also has the added dimension that it captures full waveform. And so that's one of the things that we see first, is this is a vertical frequency distribution of the point clouds. And hopefully by now you understand what that is. We've been looking at these in terms of airborne LiDAR data. It's exactly the same thing, it's just a vertical frequency distribution. No different to the airborne, it's just captured differently, that's all. What we see first of all is that the waveform-based system sees a lot higher into the canopy. We're almost up to 50 meters there using the waveform system. Well, the reason for that is because when you use discrete points, when you capture discrete points, you have to make a decision as to whether you're going to capture first returns, last returns, so on and so forth, and that happens within the system. It makes that decision. Well, full waveform actually allows you to capture a lot more information that a discrete system is never going to be able to capture. So the full waveform actually does give you a little bit more information on height. And that's exactly the same with airborne systems as well. You can usually see a lot more with a full waveform, it's just a lot harder to play with the data. Now, in terms of the vertical distribution, when we compare the two discrete systems, the echidna in discrete mode and the ILRIS in discrete mode, we see they both come up with exactly the same height. They both come and top out at the same place, which is quite encouraging. Now, you'll notice the ILRIS profile, the blue profile, is very, very smooth. The reason for that is it's a much, much higher resolution scan. I don't remember the difference off the top of my head, but it's at least an order of magnitude difference. There's at least 10 times more data density in there from the ILRIS data capture than there is from the echidna. Fundamentally, that's not a big deal. We could always make the echidna faster. That's a trivial thing, but that's why the ILRIS profile looks a little bit more smooth. The other thing to note is that the density of foliage in the upper canopy is higher in the ILRIS relative to the understory, and that more accurately reflects the conditions in the field. I don't have field data to verify that, but believe me, let's accept what I'm saying. When you look at the echidna data, we actually see that the echidna is predicting a high amount of biomass at the understory level, and we know from our own field observations that that's not the case. And so what we're seeing in the data here is that the multiple views from outside looking in actually captures better profile information. It actually provides a more accurate representation of that three-dimensional physical space. So we might conclude that maybe it's better to use multiple scans in. Well, I wouldn't conclude that, because from a logistical point of view, it takes at least 10 times more time in the field to do that. It's much more challenging to do that. And then subsequently, when you're aligning the scans and trying to extract the information, it's much more difficult. The echidna is actually far more, it's much more optimal type system. Any type of hemispherical system is much more optimal for this type of work because of the way it's deployed, the speed of its deployment in the field. You can do 10 PSPs with a hemispherical scanner in the time it takes you to use a frame-based scanner to do exactly the same thing. And that's just in the field. Then when you get back to the office, I think there's a lot more scope for automating scripts from the hemispherical. So I think from a practical point of view, the hemispherical scanners actually win out. Unfortunately, 10 years ago, when we did this PSP, but this plot-based study in Ontario, we didn't have a hemispherical scanner. We just had this first-generation frame scanner. And so I'd just like to illustrate for you how it can potentially be deployed to extract some plot-based metrics. Our objectives at the time were to improve the consistency, minimize time and subjectivity in field-based timber volume data capture. So we were really only focused on DBH height. We did also look at a few other metrics, but those are the two metrics that we were primarily interested in. Oh, and of course stem density. We have to have stem density, so we mapped stem location. And then if we could capture those metrics, those three metrics, location, DBH, height, if we could capture those, would it be possible to automate that? And so we did a little bit of work on that. So it's the range of metrics we actually captured in the field. So in the plots, in a tolerant hardwood and a conifer plot adjacent to one another, we captured a number of field metrics. And those that are underlined, we also tried to extract from the TLS data. This is actually a later generation image of the iris. It didn't look quite so funky back then. But this is what I mentioned earlier about that wedge effect of the scan. Now, in reality, so here's that. I guess it doesn't work, but point over there. Okay, on the in the middle there, that multicolored bunch of trees that you can see, I've actually truncated that scan. The scan does go all the way back to the sensor, and it does look like a wedge in reality. But what we can see here is the plot. So that's the start of the plot. The point that that little bit of geometry is trying to make, that you can see there, is that there is a minimum distance. And the challenge here is that you kind of have to a priori know what the height of your trees are going to be in order to calculate what that minimum distance is that you have to be away from the plot. Now, as a rule of thumb, if your trees are 20 meters high, you need to be just over 20 meters away from the plot in order to capture that full height range. Not so much of a problem if you captured it from multiple locations, but if you only wanted to use a single scan, you'd have to be at least that distance away. And then in the plan view, in the black and white image in the plan view, you can see the effects of occlusion or shadowing. So when the scanner hits a stem fairly close to the scanner, everything behind it is in shadow and not observed. So this was the plot setup for the two areas sampled. Not exactly ideal. This is one of the challenges with a frame-based scanner in a densely forested area, is you've got to try and locate it strategically so that you can see what you're interested in. And consequently, you end up with some scans that are, or some setups that are a little bit too close to your plot, some that are quite a distance away, and you can't optimize the angles. So it's all well and good to have this great theory where you've got three vantage points that are 120 degrees apart, because in reality, when you get in the field, you're never going to be able to set it up like that. So this again speaks to the advantage of a single hemispherical scanning system. So anyway, so that's what it looked like. And then once the scans were downloaded and aligned, we can see this is our tolerant hardware environment. What you can see here is the intensity. So clearly you see high intensities on the stems because we get full return from the stems. And then here we've got a conifer plantation. So very different structural environments. So we had to come up with some logical criteria to actually select the stems and make the measurements that we needed to make. We started off by identifying each stem by essentially truncating all of the data vertically. We took our ground layer, moved up by, I can't remember what it was, but let's say a meter, and then went another meter, extracted that 1 meter layer out of the entire data set, and then used that to identify stem locations. That works really, really well in a plantation. It doesn't work so well in a natural forested environment, but nonetheless, that was the type of logic that we were using. And then we applied a filter around that position. So once we had a stem location identified, we would apply a diameter around that and extract all of the point cloud around that point. And as a first cut on our iteration, we used the maximum diameter that was measured in the field. So if the maximum diameter we measured was 3 meters, then we would apply a 3 meter buffer to all of our points and extract the point cloud within that buffer. We could then extract those digital trees, send them to another database, and then we could manually clean them. We didn't have an automated way to clean them, but probably are ways you could automate that. And then that allowed us to populate a database of, I don't remember now, but a couple hundred trees, a couple hundred or so digital trees. And then from that point, we could measure the various attributes. So tree height being one, DBH, crown diameter being another. Crown diameter was not one we could automate. We had to manually measure that with digital calipers. tree height could be automated, because once we'd extracted that point cloud, we could simply use some logic to extract the minimum height, the maximum height, use a vector to join the two, and calculate the vector. I know that sounds kind of contrived, because you're kind of thinking, well, you know, minimum height is maximum height, why don't you subtract the two? It's a function of the way the software works. If we link those two and put a vector in there, it actually allowed us to calculate the height. It also means we can count the lead. If a stem is leading over, then it wouldn't be appropriate to subtract max and min heights, whereas a vector actually gives us the true stem length. DBH, we just extract all data that was 1.25 meters above the bottom of the stem to 1.75 meters above the bottom of the stem, pulled that out, and then we'd fit a cylindrical primitive to that. So we just run a regression analysis in the software, and we can fit a cylindrical primitive to that, and then the diameter of that primitive would be the DBH that would go into the database. And unfortunately, a lot of this stuff could be macro. Not everything. We didn't perfectly automate it, but at least the logic was in place. But some of it could be automated. And so this is what the database looks like. You can see on the left here we've got every single tree. It has its own identifier, and each one of those trees has a bunch of attributes associated with it. This is in the Polyworks software environment, which is really engineering software. And every single tree is color-coded separately. If you look down on that, now we can see the crowns associated with each tree. And of course, you can also see in the bottom part of the image there, the problems of shadowing within the crown. Some of those trees aren't complete, and indeed, some of the centers of the stems are completely missing off some of them, so it can be a bit challenging to get a complete data set. I mentioned that we measured the crown diameters. That was a very, very manual process. We didn't actually have a method for automating that. So that was just a process of getting calipers and measuring it in the X and the Y. We did do some validation on that, and at the end of the day, I mean, field measurements of crown weren't that accurate either, so it's debatable as to which actually gave better results. But when we did the regressions on height and DBH, what we found was that this is just for the hardwood scan, but what we found was generally encouraging results. There was no bias with DBH. DBH was quite accurately predicted. The height, on the other hand, was underestimated. And Nicholas alluded to this morning too, is that the problem with the terrestrial laser scanners, you're beneath the trees, you might have 20, 30, 40, 50 meters of canopy above you, and you're scanning up into it at some kind of oblique angle. Clearly, if there's much understory or any kind of foliage there, it's going to be hard for the scanner to see the very tops. And what we found was that there was definitely some bias there. Now, we didn't implement it in that study 10 years ago. But of course, if you've got good measurements of the stem all the way up, then you can do taper measurements. And so I just wanted to illustrate that. That's not that we did that, but other studies have demonstrated that you can do taper estimates, and of course, go with better estimates of timber yield. So some of the technical challenges is that with given the sample density is a function of range, that limits the plot size. You can't have a 100-meter size plot, because you might have really, really high density at one end of the plot and very, very low density data at the other end. But you know, if you're dealing with 11.3 meter radii, 20-meter size plots, you know, that kind of thing, it's not really a problem. The field of view creates some limitations in terms of distance. As I mentioned before, with a frame-based system, you've got to be a minimum distance outside of your plot before you're collecting truly useful data. Obstruction shadowing is a problem, but obstruction shadowing is actually more of a problem in the hemispherical systems when you're scanning from the inside out. However, the caveat to that is, it kind of depends on how dense your forest is, how dense your plot is. With a more open plot, then it's less of a problem. And then another one is the alignment of the scans. Alignment's not really an issue with a single hemispherical scan, if that's all you can capture for a plot. But multiple scans looking in alignment can be a very big challenge, and I'll illustrate that in a moment. So, plot height comparisons. Again, Nicholas alluded to this as well. Now, we did these are results from another study where we had 36 individual plots. We had airborne LiDAR, we had field data, we had TLS data, and we did a comparison of all of them. And what we found was that, on average, the ALS data underestimated height by about ½ a meter. The TLS underestimated by about 1½ meter. So there's quite a considerable difference there. Now the alignments, maybe a little bit difficult to see on the image on the left there, but in the upper ellipse is a shadow of a stem. Now this is a very dense, complex structure environment, and we use a combination of manual tie point choices to align the data, plus some least squares automated approaches to bring all the data into alignment. That doesn't always work, and when you're looking at one of these scans on a computer screen and you're trying to align these, it can be very, very difficult. I mean, trees, very complex structured environments, are not the most intuitive environments to bring scans together. Another one of the problems is if you look on the left, you see those semicircles that are kind of joined together at the hip. Well, obviously those are the opposite sides of stems, and they're not meant to join in the middle there. But the reason they have is because when you apply a least squares alignment approach, most of the density of the data is on the outer edge of that stem. And so when you try to pull the stems together, it's going to align on where the densest data happen to be. And so what that does is it systematically, even though it's wrong, that does give you the best least squares fit of the three-dimensional point cloud. So that's where you don't trust the automation. You've got to go back into that, you've got to kind of de-automate the process and use some kind of manual interpretation techniques. So what were the results of our little plot study? Well, I've already mentioned that there was an underestimation of height. Now, so obviously that's going to significantly bias our overall results, but DVH was pretty good. So if we're just doing a very, very simple estimate of gross merchantable or merchantable, sorry, gross merchantable or gross total volume, then if we're just using DVH, height, and stem count, then we can go up with some pretty simple predictions. I won't go through all of those numbers, but the take-home message is that given there was no bias in DVH, given there was a bias in height, we underestimated volume by about 7%, and that was actually consistent across the two types, whether it was hardwoods or whether it was softwoods. It didn't seem to really matter. We seemed to have a similar amount of underestimation. But given it's fairly systematic, we should be able to calibrate that out. So of course there's no calibration there. That's using hard numbers. This is a totally uncalibrated approach. That's just using measurements of DVH, measurements of height, measurements of stem location, stem number, and then just throwing them into a simple calculation. No model calibration at all. So given we can get to within 7% without any calibration, theoretically we should be able to get a lot closer by just applying a little bit of intelligent calibration or compensating for that systematic underestimation of height. Okay, so this was a study we did 10 years ago. I'm kind of proud to say that now there's a company in Ireland called Treemetrics, CEO Enda Kane. I spoke to this guy on the phone back in 2003, and we had a little bit of a chit-chat about this study, and he thought it was kind of neat. Fast forward 10 years, and he's actually got a company that does this commercially now. Now, their product offerings are now so more sophisticated than anything we did back then. But essentially, it's the same kind of thing. They're still extracting the DVHs the same way. They're still looking at the stem heights, the stem counts, and they've added in a few more measurements. Mainly algorithms a little bit more complex. But the point is, this is now a commercial product. You can go to a service provider, and you can say to them, okay, can you laser scan our plots? Can you measure our timber yields? Can you optimize our production chain? So this is actually a commercial product that's out there now, and there are companies doing this. Well, I'll say companies. They're the only company I know that's doing it. There might be others. But no, I'm kind of... It's interesting to see that, because I think this is where plot measurements are going. I think it's one place that plot measurements are going. Because obviously we can capture more metrics within the plot. There's some things we can't get. You know, species is always a challenging one. But definitely there's a lot of potential here, and it's great to see this being commercialized. One other element that I think is the future of plot-based sampling in the field is to use mobile mapping systems. In fact, I believe we might even move away from plots. I don't know, maybe that's sacrilegious to say that, but I think if you look at what's happened in the airborne world over the last few years, I mean, we've been collecting transects over our plots for the last 8 years now in Nova Scotia. And working with Nicholas and Mike Walter, we've been doing transects on a national scale since 2010. So, you know, this whole idea of transect-based sampling seems to be another approach to supplement plot-based sampling. So why can't we do the same thing beneath the canopy? We've now got mobile scanning systems that you can wheel around by car. You know, we could wheel a scanner around inside this room, and within 5 minutes have this whole room three-dimensionally mapped. Why couldn't we do that under the forest? I mean, it might be a different kind of car, you might have a big off-road wheels on it or something like that, but it can be done. Or we can stick it on an ATV and move around the more open forest canopy or something like that. So I think that's, it could be a bit of a paradigm shift there in terms of how we do sub-canopy field-based data collection. I think we're on the cusp of the technology is just about ready to be tested for that kind of an application. So I kind of say watch this space. I think mobile mapping is where we're going to be in a couple of years for field-based forest validation.